Quantum mechanics describes phenomena that differ greatly from our everyday understanding of the physical world. In the microscopic world, it is impossible to predict with certainty the outcome of an individual measurement. Some physical quantities do not have a definite value prior to the moment of measurement, while the laws of classical mechanics fail to give correct predictions. This raises the question, what is quantum mechanics actually built upon? Like any fundamental physical theory, it is based on several postulates, foundational statements, that are not derived from more general principles, but are accepted because they are confirmed by experiments. In this video, we will break down the postulates of quantum mechanics and see precisely how they form the mathematical language of quantum theory. The history of quantum mechanics unfolded quite differently from how it is usually taught in universities. Nobody started with ready-made postulates. First came experiments, the results of which were impossible to explain using the laws of classical physics. Scientists proposed new ideas, tested them, encountered new contradictions, and returned to experiments once again. Thus, step by step, during the first decades of the 20th century, the theory we call quantum mechanics today was formed. Therefore, its postulates are not arbitrary mathematical rules. They are a concise description of how nature actually behaves. The first postulate of quantum mechanics states that the state of any isolated quantum system is completely described by a state vector. This vector contains all the information that quantum mechanics can fundamentally provide about the system. If the state vector is known, we can calculate the probabilities of the outcomes of any possible measurements. It is important to understand that the state vector is not an ordinary arrow in three-dimensional space. It is an element of a Hilbert space, an abstract vector space, whose elements represent the possible states of a quantum system. To understand the physical meaning of this postulate, let's consider the Stern-Gerlach experiment. If we pass a beam of silver atoms through an inhomogeneous magnetic field, only two possible outcomes are observed on the screen. The spin turns out to be aligned, either up or down, relative to the chosen measurement axis. It is precisely these two states that form the basis of a two-dimensional state space. However, prior to measurement, the system does not have to be strictly in one of them. The state is a superposition of basis states, with complex probability amplitudes. Visually, for a two-state system, such a vector is specified by a point on the Bloch sphere. Thus, the state vector does not predict a specific measurement result in advance. It determines only the probabilities of various possible outcomes, while the results themselves become known only at the moment of measurement. Merely describing the state of a quantum system is not enough. To make physical predictions, we must also specify which physical quantity we intend to measure. According to the second postulate of quantum mechanics, every observable physical quantity corresponds to a Hermitian operator acting in the Hilbert space of states. That is, each physical quantity has its own operator. Position corresponds to the position operator, momentum to the momentum operator, energy to the Hamiltonian, and spin projection to the corresponding spin operator. However, it is crucial to understand the fundamental difference between a physical quantity and an operator. An operator is not a measurement result, nor a numerical value of a quantity. It is a mathematical transformation, acting on state vectors. If an operator acts on an arbitrary state, generally speaking, it transforms one state vector into another. However, there exist special states which, under the action of an operator, change only by a numerical factor, preserving their direction in Hilbert space. Such states are called eigenvectors of the operator and satisfy the equation, where the number A is called the eigenvalue of the operator. It is precisely the eigenvalues of Hermitian operators that represent the possible results of measuring the corresponding physical quantity. Therefore, finding the eigenvalues and eigenvectors of operators is one of the central tasks of quantum mechanics. Observable physical quantities in quantum mechanics correspond to Hermitian operators. Hermitian operators is defined by the condition shown on the screen. In matrix representation, it involves transposing the matrix and complex conjugating all of its elements. Why do Hermitian operators play such a crucial role? First, all eigenvalues of a Hermitian operator are real numbers. This is fundamentally important, since the result of any physical measurement must be a real number. Position, energy, momentum, or spin projection cannot take complex values. Second, the eigenvectors of a Hermitian operator form a complete orthonormal basis of the Hilbert space. This means that any state of a quantum system can be expanded in terms of these eigenvectors. After performing a measurement, the system can transition into only one of these eigenstates, and according to Born's rule, the probability of obtaining the corresponding eigenvalue is equal to the expression shown on the screen. That is precisely why Hermitian operators allow us not only to determine the possible measurement results, but also to calculate the probability of each of them occurring